All right, so taking a look at another one. Okay, this one basically starts off that a ball is thrown upward. A ball thrown upward. A ball is thrown upward. What is the maximum height? Its initial vertical speed is 9.7 meters per second, and the acceleration of gravity, the acceleration due to gravity, they tell us is 9.8 meters per second squared, and that we should, quote, ignore air resistance. Now in class, we usually use 9.81, but in the online system, since these are the numbers it uses, if it says 9.8, go ahead and just use that instead of the 9.81. There's a good bet 9.81 won't throw it off enough, but never hurts to use the numbers they specifically give you. In class, however, we like to use 9.81 for 3 significant figures, because that's kind of our rule. Okay, so we've got a happy person here, very happy, and they take a ball and they throw it up into the air. And it goes up into the air, and they say that they want to know what the maximum height is. So basically, if I throw this ball up into the air, its maximum height was about up here. Goes up, and then comes back down. This one's a little tricky, because it almost seems like they haven't given us enough information. Let's go through and write down our information. It's a kinematics problem. So, since we're dealing with up and down, I'm going to call this delta y instead of x. X is usually horizontal, and y is usually vertical. So this is delta y. And we're going to do v final, v initial, acceleration, and time. Now, the acceleration they gave us is 9.8 meters per second squared, but they say it's the acceleration of gravity. Gravity has a tendency of pulling things down. Remember, each of these is a vector except for time. So 9.8 is the magnitude, the number. But since these are vectors, we also need the direction. Down. Negative for the y direction. At least that's what I'd recommend. All right, they say that this person starts by throwing the ball upward with an initial velocity or an initial vertical speed of 9.7 meters per second. And here's where we want to bring that in. Technically, they're right to use speed, but the diagram they give us shows that they're throwing it upwards. For velocity, we want the actual vector, which means if it's going upward, then it's, well, positive. So we didn't actually have to write that. But if we threw it downward, this would be a very different problem. You'd need to put a negative in there. It's not downward, so just keep track of that. In the future, you may have a problem where that becomes important. Your initial velocity might be downward. I could be throwing it down. In this case, I'm throwing it up. Great. If you misplace some of these negatives, if you forget to keep track of direction, you might end up with answers that don't make any sense. All right. And they want to know, they want to know how high up it goes. We want to find delta y until it goes, let's see, it's going to fly up in the air and then come back down. So we want to find this, delta y. It's going to start here from some height, we could call that 0, and we want to find up here y. We can find that by having delta y because our initial would be 0, so final minus initial delta y would just be the same thing. So we're trying to find our delta y here. Well, wait. We've only got 2 pieces of information. Did they tell us how long it takes? Ball's thrown upward. I don't see anything that's a time. No minutes, no seconds, no hours or years. I mean, could it take a year? I don't know. Time is the thing I'd probably expect to go for. What about my final velocity? I need one more piece of information in order to try and solve for delta y, because delta y is what I want. Time, well, I don't know. Time isn't listed on here. All right, maybe it's the other one. Maybe it's final velocity. But they don't tell me what the final velocity is, which is where things change a little bit from math classes. Remember, in physics, we use math to solve real problems. We're going to talk about things in real life. I want you to watch this. The ball, it goes upward. Down here, I'm throwing it with a velocity upward, but when it gets to the highest point, how fast is it going? Goes up, slows down, slows down, slows down, stops at its highest point, and and then it falls back down. How fast is it going? Its final velocity when it gets to the maximum height. Slows down, slows down, slows down, slows down, stops, and then starts falling back down. This is one of the common things many people overlook because it's information that is almost never told to you. Because you have to stop and think about it. When things get to their maximum height, their velocity in the y direction is actually 0 because they're going up, going up, going up, positive velocity in the y. Then they come to a stop, 0, and then they start falling back down, negative, negative, negative. Well, the highest point they get to is right when they stop. The missing information is that your final velocity is 0 meters per second. Think about it. How fast is it going when it gets to the very top? Now, it's just for an instant. But that's where it changes direction, so its velocity is positive, goes down to 0, and then becomes negative. All right, now that we've got that, that's the hard part. Now that we've got that, let's see what we can do. We've got 3 pieces of information we don't have and don't care about time, at least right now. So we're going to go with the very last equation. That's going to be v final squared equals v initial squared plus 2a delta x. That's exactly as it shows up on my equation sheet. In this case, instead of a delta x, we're actually using a delta y. That's totally okay. We know that that's what we're solving for. Well, I can take my final velocity, which is 0 meters per second, quantity squared. That's my final velocity. At the very end, it's way up here. Equals my initial velocity, positive 9.7 meters per second, quantity squared, plus 2 times negative 9.8 meters per second squared. I apologize, I'm running out of room. Times, I'm going to call it delta y because I'm putting in my values. This is finally where I'm going to solve for what I want. Here's where if you forget this negative, then your equation's going to start acting real weird real quick. You're going to get a negative delta y, which means it's somehow going down. Anyway, signs are important. These are vector quantities. All right, well, we end up with 0 meters squared per second squared equals 9.7 squared, 94.09 meters squared per second squared, minus, let's see what's that going to be, 9.8 times 2, just to be certain, minus 19.6 meters per second squared times delta y. Now, you can go through and you can do algebra any way you want. I like to get rid of negatives, so I'm going to add this over to the other side. I add 19.6 times delta y, including some units, but I'm going to be a little lazy right now. 19.6 delta y. Whatever I do to one side, I do to the other. That cancels out that, and we get the following. 19.6 meters per second squared times delta y equals 94.09 meters squared per second squared. Last step, we want to get delta y by itself, divide by 19.6 meters per second squared. Real quick, watch what happens to the units. Well, meters squared per second squared, the per second squared on each of those cancel out, and one of the meters cancels out, so we end up with, you're gone. Delta y is going to be equal to some number that has units of meters. Once again, put SI in, you get SI out. So I'm going to take 94.09 divided by 19.6, and I find that delta y, the maximum height, is equal to 4.801. That's way more significant figure, so I'm going to do 4.80 meters. Let's see what they've got for me. 4.80, yep, 1. There you go. Now, the difficult part of this one is they don't seem to tell you all the information. This is where you got to remember we're dealing with real life. Sometimes the information isn't obvious, but it's there.